I do a C0 gate? Can I do an X gate? Or there is a fundamental limitation that is preventing me from achieving the performance of some desired gates. The problem with the controllability studies is that most of this research here is very idealistic. So we assume things like there is no noise, the system is closed, or the evolution time is unlimited. In reality, these assumptions are not true. Like the device operates in a finite time scale. There will be noise, and so most of the results in controllability are actually very theoretical, and they don't apply to actual devices. So this is one of the fields that we should actually, as a community, look more into it. Now, assuming we know that the device can do whatever is needed from, then what we can do next is control. So I'm designing some pulses, for example, to make the device operate and have some Zardark, like a quantum gate. And what should happen is that this should be like a cycle. So after control, we should assess the performance of the device and then go back to the original design and make it better. And we keep going going in this cycle until we have the behavior of the device is good, like the performance is as good as we expect. So today I'll focus on two stages, the identification and the control. So this will be the focus of the talk today. Oops. Sorry, I think I lost my screen. Okay. Okay, so let's start by talking about identification. So if you want to abstract what we do, we have, like, if you think about any quantum device, we'll have the abstraction is the following. We have some control pulses that we can apply, like magnetic fields or voltages, and we have an observable. Observables like something that we can measure in experiments. And when we do the design, we have a simulator. The simulator will take these pulses and predict what the observables should be. And so this would be like, for example, this simulator will solve Schrodinger equation and simulates the evolution of a quantum system. So this is one side of things. And then we have the experiment, the actual device, the fabricated device. So we can use the same abstraction. So we can think of it as just a box where we apply pulses or whatever control voltages, anything, and we have some measurements. And if our simulator is good, then these two measurements should be the same. The prediction of the simulator and what I actually get from the experiment should match. If they don't match, then my simulator is not good. It's not modeling the reality of the device. So the target we have is to use machine learning. So when you have machine learning, you can have a model where you have the pulses and the observables, and you want this model, this machine learning model, which is at the end just a piece of software on your computer. We want this model to predict the observables and to match the experiment as close as possible. If we are able to have this machine learning model, then we can use it as a simulator. We can use it to replace the experiment, and we can use it to predict observables, to do control, to do anything we want. So essentially, it's a replacement of the actual device. So you have a piece of computer software that replaces your device. And so this is why we need to train the model on experimental data. So the model, this machine learning model has to be trained on actual characterization data that we collect from the experiment. So there are many ways you can do this machine learning model. So the first approach is what we call a white box, which is the basic curve fitting, the basic procedure you do in any physics experiment, which is you go, you collect some points, you plot these points, and you fit a curve. Okay, so this is, you can consider this as also like, because we are training a model, you can consider it like a machine learning model. We call it a white box because we know everything. We have exactly the equations that relates the inputs and the outputs. And so this gives you the full physics picture, gives you everything. And this is the best thing that you should start with, actually. The problem occurs when your models that you are using, the equations that you are using, are not accurate. And this can occur for many reasons. For example, you usually do approximations for material properties, okay? But in the actual thing, the actual material, there's a complicated crystal structure, and we cannot really simulate everything in the crystal, just take approximate models. Or sometimes we just, the dynamics are complicated, so we assume something about the noise that is affecting the system. It's just to make the equations easier to deal with. So there are many situations where we would use simple models so that we can write equations, but then the reality is different. And this is where the discrepancy happens. So the other solution you can do, the other approach, is to use a black box, the complete opposite. So a black box, like a neural network, is just a nonlinear function, like this function you have here. So people in machine learning love to use these kind of pictures to show architectures of neural networks, but you can think abstractly as just a nonlinear function. And you have some weights, and these weights are trainable. So as you can see here, there is no physics at all. It's just abstraction. It's just the fact that if you have some function, then you can approximate it with just a general nonlinear structure. So the theoretical foundation of using neural networks is a theorem called the universal approximation theorem. It tells you essentially that if you have a map between two compact spaces, then there exists a neural network that would approximate this map. And then so this is the theorem, and then the job of a machine learning engineer is to find the neural network that actually satisfies this. So as I mentioned, there is no physics there, and this actually could solve a lot of problems. Like sometimes you don't really need to know the details of the model, you just need something to model the relation between inputs and outputs. Okay? And so in classical world outside of quantum, this works very nicely in applications like image recognition. If I want to write a software to detect cats and dogs in a picture, there is no equations, there is no physics. You just want to do the job. You just want the computer to find cats and dogs, okay? So this is why people invented neural networks in the first place. When we use neural networks in physics, we have, again, it's according to what we need in our application. Sometimes it's sufficient just to model inputs and outputs, so you don't care about what's happening inside. Sometimes it's not sufficient. You need to know something more. So far we have seen two approaches. Then we have the white box approach, which is the full physics, right? Every equation you can think of. And the black box, where there is no physics at all, just abstract mathematical structures. And so what you can do is to get the best of the two worlds, which is the gray box. So in a gray box structure, you have your neural networks, and you also have layers that are just the laws of physics that you know. Like, for example, I don't need a neural network to discover Schrodinger equation. We all know Schrodinger equation, and we've been using it for 100 years now. We know that it's correct and it predicts everything correctly. So just write down Schrodinger equation. You don't need the neural network to discover it, okay? Or for example, if I am doing measurement, we know how to calculate the measurements, how to calculate observables given the initial state and the unitary. So whatever you have, you know that you are certain of, you just put it there in the white box layers. And whatever is unknown, you put it in the neural network. So in this example here, the neural network predicts the Hamiltonian. I don't care in this application, I don't care about the exact equation relating the voltages with the Hamiltonian. I just need the neural network to discover this relation. But once I get this Hamiltonian, then calculating the unitary and the measurements and everything, we just follow the rules of quantum mechanics. So I don't need a neural network to discover all this. I can just hard code these equations directly.
Sorry, is it okay to interrupt this point?
Yes.
So your neural network can be thought of as a bunch of quantum systems that are interacting. Is that right?
I think of it as more like just a mathematical structure, like a nonlinear function, like this one. It's just a bunch of nonlinear functions that are complicated, that they can model any relation, can approximate any relation.
Okay, so it's more of a classical system.
Yes, yeah, it's a piece of software essentially. Like, yeah, it's classical.
Okay, and it's meant to mimic your actual physical system.
Yes, exactly.
But is there a feedback in your schematic that you showed?
So the feedback comes from when I do the training. So when I do the training, I'm trying to minimize the error between the predictions of the neural network and the actual measurements I get from the experiment. So this is the training process. I'm trying to find the weights of the neural networks, such that it predicts correctly the output. So the feedback is done during the training.
Okay. So that will sort of decide the weights and the subsequent iteration.
Yes.
Okay.
Yes. I'll talk about the protocol in a moment, how we train these neural networks. Okay. So this is no worries. So this is the idea of the Graybox. So we combine neural networks and in other machine learning structures that people invented in the classical world alongside layers of physics that we are certain. So once we have this model, how can we use it to do control? Well, because it's a piece of software that can be used to predict the behavior of my device, I can just use it to numerically optimize the pulses or the voltages I have. So I just put it in a numerical optimizer like a grape algorithm, for example, and using the predictions of this model, I can find the optimal pulses that is needed to have some target. So the idea here is after the identification, we replace the device with the machine learning model. And again, in this talk, I'm focusing on the Graybox because from the Graybox, you can extract things that are useful for control, like noise operators, Hamiltonians, unitaries, etc. If you have a neural network that just gives you the observables, it doesn't give you any information about like what is the unitary, what's the Hamiltonian. So what if you want your target to be some gate, some quantum gate, an X gate, for example? The neural network in this case wouldn't be very useful. So the use of the Graybox allows you to have access to some physical quantities that have a meaning, and then we can use these quantities in our optimization procedure. Okay, so the next part I want to see. I want to show some of the results we have on this basic idea. So just to give you a quick overview of how this started. So back in 2018, we started looking into photonic systems. So this can be modeled as a time-independent closed system. And this was the start of having this Graybox idea. And even though the concept has been in classical control engineering for many, many years, it's not new. It didn't exist really in the quantum world. And one of the reasons is that the Graybox is like when you write the software, you have to do the training, and the training requires calculating gradients. And with quantum mechanics, when you have unitaries and complex numbers and stuff, it was difficult. Around 2018, Google had TensorFlow. So TensorFlow facilitated actually actually implementing Graybox, because in TensorFlow there is something called auto differentiation, which is essentially a feature to calculate gradients automatically for you without you having to write code to calculate derivatives. So this made the idea of implementing a Graybox in the quantum world possible. So this was our start in this research, and then later we generalized the proposal to open quantum systems. So when you have a system that is that's affected by noise, then we extended this to an architecture called a spectator architecture. I'll talk about it later. So this is a way to increase the throughput of quantum computation. Then in 2021, so this was all theoretical essentially. In 2021, we did actually the experiment. So we did the full protocol where we train a Graybox and then use it for control and assess the performance of control. And then recently we looked into more detail into the control aspects of using the Graybox, like focusing more on control. So previously it was more focused on identification. In this work, we're focusing more on control. So I'll give a quick overview on these different results that we had over the years. So I'll start with this one, with the experimental results, because these are very interesting. So what we had is this device. This is a photonic device, a waveguide array. So it's a device where you can put light into one of these input ports, and it propagates, and then the light goes from the output ports. And there are electrodes, and these electrodes can be used to change the behavior of the apply voltages. This changes the behavior of the material inside here. And as a result, you can control the propagation of the light. So you can have light going through here, coming from here, or maybe split 50-50 between this port and this port, and so on. And if you are putting like single photons, then this becomes like a quantum device. You can do quantum gates with it. So the problem was that we wanted to characterize this device, because the models that are usually used in the literature in photonics were not matching the experimental results, the experimental characterization. So we did the idea of the Graybox. So we designed the Graybox, and the protocol for training a Graybox goes as follows. So we start by creating a data set. So a data set is a set of inputs and outputs. So here in this case, I generate some like random voltage, and I go to the lab. I put lights, put this voltage, and measure, and see how much power is coming from the output ports. And then I generate a new set of random voltages and repeat the experiment, and so on. So I create a data set of these pairs, different voltage configuration, and I see the different power distributions I get at the output. And this is similar to measuring probabilities of a quantum state, essentially. So it's like measuring the sort of doing tomography on the state. So this is the first step. So I create an experimental data set. The next step is I train.
Sorry, your ket 0, 1, 2 are polarization state.
So here the encoding is space path encoding. So if I put the photon here, then this is ket 0. If I put it in the second port, this is ket 1, and so on. And so it's path encoding.
See, okay, it's more spatial kind of encoding.
Yes, yeah, exactly, yeah, spatial, yeah.
So you would, it's still, you regard it more as a classical state, because it, or would you call it a quantum state? Because
so it's the device. So if you put single photons, then the device like behaves as a quantum device. So we model it as a quantum device essentially. So we have Hamiltonian, unitary, and the unitary is related to the Hamiltonian by solving the Schrödinger equation. So we model it as a quantum device.
One more thing, this device is the core of this waveguides are lithium niobate, right?
Yes, yes.
Right. Okay. And the single photon sources that you have used is what is for this
So here
experiment?
in the experiment, we didn't use single photons. We used laser, just laser source. But in principle, you can also operate single photons. So the statistics will be the same. If you operate with continuous laser or single photon laser, you will get the same statistics at the end. So in this work, we were focused, like we just used the usual laser.
Coherence. Okay.
Yeah.
Okay.
Yeah.
Thank you.
So the material, this lithium niobate material is like if you apply voltages, you can control the refractive index. And so this is the idea of the operation of the device. So by applying electric fields, you change the refractive index, and so you can change the propagation in these different wavelengths. Okay, so once we collect the measurements, we train the Graybox. And the training is the following. Like we start to remember the Graybox has two parts, a neural network and some physics layers. Okay. So when I'm trying to minimize the error, when I'm trying to make the Graybox predict my experiment, what I do essentially is minimizing the neural network, because optimizing the neural network, because the white box layers, there is nothing to train, like calculating the evolution, the unitary given the Hamiltonian. It's just to write down the law, the physics law. So there isn't anything to train there. And so when you try to minimize the error, it enforces the neural network to generate like the correct output, which was in this case the Hamiltonian. And we train the Graybox over this data set. And then we test the Graybox. So how do we test it? We put as an input, so we have the model, we make the model predict a set of new voltages. So these new voltages were not in the training set. And this is important because we don't want the neural network to memorize the examples you have. We need to have a structure that generalizes. So if I put new inputs, it can correctly predict the outputs. So this is what we do. We test the Graybox. We give it a set of new voltages that have not been trained over, and we see the predictions and compare if the predictions match the experiment or not. And then finally, we can use this to do control, because as I mentioned, once you have the Graybox model, you can just put it in an optimization procedure to find the voltages. So in this case, I want to find the voltages that I need to apply such that I get a particular quantum gate, some distribution at the output. So the results were quite interesting. So if we look down here, this is a Vinon plot, so it shows you the statistics of the data set. So this is the median, the maximum, the minimum, and this is like the distribution. And we are comparing the three architectures, the Graybox, the white box using the equations that are common in photonics, and the black box, which is just a neural network with no physics at all. So we see that the training, the MSE is the mean square error. So this is the error between the prediction and the actual measurements. So we see that for the gray box and the black box, they have low MSE, so could predict good predictions, but the white box is not. And so this is an indication that the equations that we use in a pure white box do not match the reality of the device. The next part here is the testing. So this was the statistics on the training set. This is the statistics on the testing set, and we see that there isn't much difference between the MSE level. So this is a good indication. It tells you that your machine learning structure is generalizing. It's not memorizing the examples in the training set. It can still predict things that are new. And then for the control, we had two controls. So first one is output control, which means I have just a distribution. I want, for example, 50-50-0 or 20-30-50 or whatever distribution here. So this is output control. And then we have unitary control, which is you want the whole device to act as a particular unitary. So this would be like a unitary over, so like over all input states. So for the optimization here, we see for that the results also are like very promising. We get a low MSE for the gray box and the black box. For the unitary control, we cannot have a black box because remember that the black box, the neural networks, there is no physics. So you cannot ask the neural network to prepare a unitary. It doesn't know what a unitary is. It just knows inputs and outputs. So input voltage, output probability distribution. There's no unitary information there. So this is an example where just using a neural network on its own is not sufficient for your application. The above figure here shows also the statistics of the fidelity. So how many, so we're running the control over 1000 randomly generated gates, and we're looking into the distribution of fidelity. So you see here that for the Graybox, we have like very high fidelity with a very, like most of the examples had very high fidelity. So this was very interesting because we actually did the experiment. So the thing about machine learning is that in principle, you can do everything with machine learning, but you have to do it, you have to prove it. And simulations are not sufficient because in simulations, I am controlling the simulation, whereas in reality, the device would have things that like some a random behavior, there will be noise, there are things that you don't actually have in your model. So in this kind of research, it's very important to test on actual devices to know the performance of your algorithms, whether they are performing well or not. So this is the one of the main results we had, experimental results. Okay, the next thing I want to talk is a different application, and here we're talking about open quantum systems. So in this work, when we model photonic devices, we model it as a closed system, and it's also time independent. So the photon propagates very quickly. You cannot change the Hamiltonian faster than the time it takes to propagate from input to output. Then
I just have a quick question. So what kind of errors did you notice affect your physical system actually, the photonic system?
Yeah. So there were a few things. So first of all, the model we used that is common in photonics is that the relation between the voltage and the refractive index is linear. So there is a linear relation between voltage and refractive index. That's one thing. The other thing is that the Hamiltonian is real valued. So all the entries in the Hamiltonian are real numbers. And the third thing is that the Hamiltonian as a matrix is in a tridiagonal form. So I have main diagonal and one off diagonal up and down. So this is the basic model that is used in photonics, like in textbook models. When we use this model as a white box, it didn't give good results. And throughout the experiments, we realized that first of all, the Hamiltonian is not necessarily tridiagonal. Like there can be coupling between the waveguides further than the nearest coupling. The other thing is that the linear model that we use for the voltage is also not probably not accurate. So it's not linear, it's non-linear. And the third thing, and that is the most important, I think, is that the Hamiltonian is complex valued. So we trained the Graybox first with enforcing the Graybox to generate a real valued Hamiltonian, and this wasn't fitting the data. And so when we relaxed this and allowed the Hamiltonian to be complex valued, which is allowed by quantum mechanics, it actually fitted better. And so this was an indication that, okay, these kind of devices, we need to model the Hamiltonian as complex valued, not just real values. So in terms of modeling, this was very interesting because now we have like a different set of assumptions like that you like. It's not in the standard textbook about like materials and stuff. Yeah, so
Okay, that's interesting. So when you add complex terms to your Hamiltonian, it just means you're changing, you're affecting your coupling in a certain way, right? So
Yes.
what does it actually mean to say complex?
So what I think probably is happening is the following. If you see this, the architecture of the device here, there is like a fan in and fan out. Like it's not straight waveguides from beginning to the end. And we have to do this fan in because these are ports that have to be connected to optical fibers. So they have to be separated with some minimum distance. So you can actually couple the chip to the optical fibers, okay? So what I guess is happening is that the overall, like when you have the fan in and you have the main part of the waveguide array, the straight part, and then you have the fan out, these unitaries, like these three unitaries do not commute. And as a result, if you look at the Hamiltonians, like the Graybox is trying to find one Hamiltonian to model the overall performance. So somehow it has to be complex. Like it cannot just be real because there are many components. It's like taking, you know, the logarithm of some effective unitary. So there is no reason that it will be real valued. If it was just the straight waveguide, then possibly it can be real. But because it's not, there are like different parts, then it's trying to learn an effective Hamiltonian. So this is why you get the complex term. It's kind of an effective Hamiltonian.
Okay. Thank you.
Of course. Okay. So the next project we looked into is, okay, how to extend this to open quantum systems when you have noise. Okay. So the evolution is no longer unitary. It's just described by a CPTP map, a channel. So, so if we look at what Hamiltonians look like in this situation, you'll have like a control Hamiltonian. So you have like a drift. This is like a qubit, okay? So you have the Paulis and you have control over the Paulis and you have a drift term. And you have a noise. So a noise term would be like a stochastic Hamiltonian. So this is a Hamiltonian where you have these betas are random process. So they are just random signals essentially. And when you evolve this, like the control Hamiltonian and the noise Hamiltonian together, and you take the average, the averaging will induce the non-unitary dynamics. So the problem with open quantum systems is how to write an equation to describe the dynamics, okay? Most of the equations that are used are only valid under some assumptions. For example, the master equation, the Lindblad master equation, is only valid for quantum Markovian noise. If the noise is non-Markovian or non-quantum, you cannot use a master equation. So just writing down equations for open quantum systems is a challenge on its own. It's a field of research, how to write dynamics. And so the use of a white box is already a problem because what's the equation? We don't even know the equation. So in this work and collaboration with Gerardo in Griffith University, we have developed this theoretical framework. So here we're looking at the expectation of some observable. So it's, if you know, like from the basics of quantum mechanics, just a trace of u rho u dagger times O. So u rho u dagger is just the evolution of your state, like Schrödinger equation, and O is your observable, whatever you are measuring, and you take the trace. What we have extra here is this term that we call the VO, the noise operator. And what we did is to show rigorously that any quantum system, any open quantum system can be written in this form. So it looks very similar to a closed system, just having this extra VO. VO is a system operator, so it lives in the Hilbert space of the system. And if you know it, then you know the effect of the noise on your system. So the advantage of this formulation is the following. In realistic systems, your noise, especially in the quantum case, will be just like a quantum bath. And this quantum bath is, you can model it, for example, as a bunch of harmonic oscillators. So these harmonic oscillators have an infinite dimensional Hilbert space. So if you want to write an overall evolution, it becomes complicated mathematically because you have to deal with infinite dimensional spaces, and it becomes a whole mess. In this formulation, you just take whatever information is needed from the path and how it affects the system. So this is all compressed, all encoded in this operator. And so if you have a qubit, this will be just a 2x2. So it's very nice because you don't need to describe the path or how it evolves or the state of the path. You just need this operator. And if you know this operator, then you can do all the tasks in control. So you can do dynamical decoupling, which is noise cancelling essentially. So what you want is that this VO is identity and that your evolution is just row zeros, like identity gate. So this is quantum memory essentially. Or you can have a target quantum gate. You want your evolution to be some target G. So in this case, you have two objectives. You want to cancel the noise, so VO goes to identity, and you want the evolution to be described by G. And you can do also noise spectroscopy. So noise spectroscopy is understanding the behavior of noise. So it turns out that also given this VO, you can unpack it and find the properties of your noise that's affecting the system. So it's a very nice framework. And again, the nice thing is that you can prove rigorously that it works for all cases, whether it's Markovian or Markovian, classical quantum, all sorts of noise, it still works. The
I have
price,
a question.
yes.
Just a question.
Yes.
What is the nature of this VO matrix? Does it look more like a unitary or Gauss operators, or like?
No, it's general. It's a general operator, so it's not.
It can be anything. Like it can be non-Hermitian. It can be.
Yes.
It can be complex, and like it's just a general matrix. It can be anything, right?
Yes, there are some properties. So in the paper, we derive the properties, but it's not like the standard thing. So it's not unitary. It's not a gate. It's not a channel. It's not any of the standard objects you see in quantum.
So wouldn't it be constrained by at least physical realizability of a quantum system? You know, physical realizability is. So you cannot have an arbitrary matrix representing a quantum system, right? So it will be at least constrained by some sort of physical realizability of quantum system, right?
Yes, so it is actually, because if you write down the equations, it is the average of unitaries. It is, you can write it as the average of unitaries.
Okay.
So the trick is the following: you move the interaction picture, and then you do some magic, some math tricks inside the interaction picture. And the idea is to collect all the terms that affect your system in one bunch, and then take the average over this bunch. And this gives you the VO. So it's constrained naturally because it comes from taking average over unitaries.
I see. So it's similar to the notion of Gauss operators, isn't it?
Yeah,
because in some sense, summation of Gauss operators, they sort of resemble a unitary, although it's non-unitary evolution. So
yes.
All right. Okay.
Yeah.
Carry on. Thank you.
And this actually raises the following question: how can you calculate VO theoretically? And then we have the problem, the price to pay. Like, this is a very nice presentation, but again, if you want to calculate this by equations, you have to use like some approximations or some assumptions, because otherwise this VO includes inside it the unitary of the noise or the path. And this is the difficult object to deal with. And so some of the work that has been done with this framework is in special cases, like if your pulses are ideal pulses like Dirac delta, or your noise is Gaussian, like some particular cases where we can actually calculate VO by hand. So what we did is to use machine learning, because I don't care about the actual equation relating VO to my control. I just want to have a piece of software that calculates it. I give it the pulses, it gives me VO. That's all I need. I don't need an exact equation here. I just need something that calculates it. And so we can use the idea of the Graybox. Again, here, you see here that U control is the control unitary. So these are the pulses. I know the pulses. I'm applying the pulses. So I can just calculate the unitary of the pulses. Rho at 0 is the initial state. I also know the initial state. And O is the observable I'm measuring. So all of these things here and the trace, all these things I know exactly. So I can use this as the white part. And the VO itself would be the neural network. So the neural network will be used to estimate VO. And then the overall architecture becomes a Graybox. And so instead of just putting a neural network to predict the observables, I make it a Graybox. I make it understand that there is a VO. And so the architecture looks something like this. So again, in the input, I have pulses, and the output, I have measurements. And I have two paths here. The first path constructs this unitary here, so Hamiltonian unitary measurement. And the second path here, we have the neural networks. So the neural networks would estimate a VO. And this VO construction layer is to ensure the constraints that we just talked about, that it's actually a matrix that comes from an average of unitaries. So you enforce your conditions here. So the neural network knows that it needs to generate this output. And you follow the same protocol. So you create a data set, you have your qubit, you apply pulses, you measure Pauli's, you train your Graybox, and the same, you test the Graybox, and then once you have the Graybox model, you can use it for control. So again, the nice thing about the Graybox is that, remember, this is a piece of software, so I can just know what is the output here. I can just write down my code to generate the output at this layer, and this would be the VO. So then I can take it and put it in my optimization procedure to do controls. What we did then with Hendra at UNSW is to study more the control aspects. So this was more the identification. In this work, we're looking particularly into the control, and we took here a model of non-Markovian quantum path. So it's a little complicated model. Without going into details, because I think we're running out of time. So this is just like a model that will induce dynamics that are not the usual dephasing that you see. It's non-Markovian, and the dynamics are very different from a standard dephasing noise that is usually modeled. Okay. So what's important is that, again, we trained the Graybox on a synthetic data set using that non-Markovian model. And we studied the performance of the control over a universal set of gates, so identity, Pauli's, Hadamard, and the rotation. And we're calculating the process fidelity. We want to see the fidelity of the control after we use the Graybox for the pulse optimization. And so we had some interesting results. So first of all, we tried single axis versus multi-axis control, and we found that multi-axis control is much better, actually. And this is something, so if you know something about dynamical decoupling, the standard techniques, like CPMG sequences, for example, you just apply it in one axis. If you have dephasing noise, you can just apply pulses. So if the dephasing noise is in Z direction, you apply pulses in X. And this is in some situations would work fine. In this kind of noise that we used to simulate the noise is complicated. So the single axis control wasn't performing well at all. So multi-axis was better. And this actually reminds us back again with the idea of controllability. That if you follow the basic controllability criteria, tells you if you have a qubit, you only need 2 Pauli's. So if it's drifting in Z and controlling in X, this is sufficient to get any unitary. But when you have noise, complicated noise, these results do not hold. Okay. The other thing we noticed is that the control constraints, like the maximum amplitude, affects also the performance, which we would expect anyway. So if your pulses are limited, then your fidelity is also limited. And this reminds us again with the idea of the cycle, the engineering cycle. So if I'm working in the lab and I have a microwave generator and it has a maximum power, and I find that, okay, my maximum power is not giving me the fidelity that I need, then my conclusion should be, okay, let's replace this microwave generator with the one with higher power. or maybe in another situation, it's not the power, maybe it's the evolution time. So this study of controllability is very important, and we need to focus on it more as researchers, actually.
Just one more question, Akram, here.
So it's more difficult to control. The remarkable thing is the cost function. So we tried different cost functions, and this changes the performance a lot. So
I just have one question here.
yes.
What axis do you refer to when you're saying multi-axis or single axis? What is this axis for?
So where the pulses are, so single axis is like Pauli. So your Pauli's your pulses are in the x-axis in the Pauli.
Right. Okay.
Multi-axis is in x and y.
All right. Thank you.
Yeah. Finally, we checked also the finite sampling. So in an actual experiment, we repeat, like we do a single shot measurement and then repeat for multiple number of shots and then take the average. So we found out that while this affects the identification, because like this is statistical noise, it doesn't affect a lot the control. Like the fidelities we get are very close to each other. And so this is interesting because then like we don't need like very high number of shots to do this experiment. So this saves actually time, the experimental procedure. Also, we tried like genetic algorithm versus t-base descent for the pulse optimization, and also there wasn't much difference. So the Graybox somehow is good, like whether any type of optimization works actually. So even if you fall in a local minimum, it's not an issue. You just get good pulses anyway. And so this is actually interesting. So now we have like a tool that we can use to study open quantum systems and do control with this framework.
So your optimization techniques that you use, the algorithm that you choose, it finds out the local minimum or global?
So we used both. So the genetic algorithm finds a global minimum, and the gradient descent finds a local minimum, and the performance of both algorithms were very close. So we couldn't find a clear advantage of doing the genetic algorithm and finding a global minimum.
So by any chance, do you pose your problem as a convex optimization?
I don't think so. It's very complicated, actually. I don't think it's convex.
Because you said the local and the global are very close.
I mean, in terms of the fidelity. So when we calculate the fidelity at the end, we didn't find much difference.
Okay.
But I don't think it's convex because the loss function is complete when you calculate the VO and then you want to optimize it. And I don't think it's convex. Yeah.
Okay.
So this is one of the things that we should also look into. So we chose in this study, we did like a few cost functions, but it's not everything. We just tried a few of them, but there are many options. We have this more detailed in the paper, but this is one of the things that we should look into as well. What is the best cost function? And the thing is that with machine learning, because you have neural networks and stuff, it's quite complicated. So there might be one cost function that performs better than the other. They will not be all equivalent. And there, again, the reason is that we have the neural networks there in the Graybox. So the neural network is non-convex. So things get a little complicated. But however, it's just now we are moving into like just the field of optimization numerics. We have a software to use that is trained to predict the behavior of an actual device. So this is the main advantage now. We can do our study of control in detail on a software that predicts an experiment and not just an idealistic model. The last thing I want to talk about quickly is this idea of the spectator qubit. So here we were looking into increasing the throughput of a qubit. So what happens in an actual device is that you need to do calibration every few hours, okay? And so you have to stop your computations. So you have to stop the computation and see what's the noise now, and then find the pulses, the optimal pulses, and then resume the computation. So the protocol we had here in this work was to add another qubit. We call it the spectator qubit. It sits physically near your qubit so that they are affected by the same noise, the same environment. And instead of measuring your data qubit, your main qubit, you measure the spectator. And you measure it and then extract information from it, from which you can say, okay, I know what the noise is that's affecting the environment, and then I can apply the optimal pulses. So it's a kind of a sensor, essentially. And again, here we used the Graybox model, and the use of the Graybox makes it actually easy to design the protocol, because it becomes very similar to machine learning in like detection, like classification, because the assumption here is that you have a bunch of noise profiles and you want to know what is the current noise profile that's affecting the qubit. So with the use of Graybox and this VO formalism, we can actually transform the problem into a classical classification problem. And we did like a few studies there to see like the performance of such a protocol. And one of the results interesting results here is that sometimes you'll have different noise profiles. Like you plot the spectrum of the noise, two noise profiles, and they are different. You see, oh, the spectrum of the first noise is different from the spectrum of the second noise, but they actually affect the qubit the same. So there is no point of distinguishing between them because it's the same. The dynamics of the qubit will be the same under these two different noises. And this depends on the control. So it depends on the constraints of the control, the pulse shapes, and so on. So this was also like an interesting point, that when we study the dynamics of the systems, it's you can have different noise models that will generate the same dynamics. Okay. And it depends on what your control is, what's the pulse shape, what's the constraints in the control, and so on. Okay, so to sum up, we started with talking about the engineering cycle. So you start by designing, fabrication, and then you characterize the actual fabricated device. There is the point of controllability that I always say we should look more into. And then you do control, and we need this to be in a cycle. So we don't want to end at characterizing the device and publishing a paper. What we should be done is then trying to design better devices based on what we measured, okay? In identification, we talked about three approaches: the white box, which is just curve fitting. This gives you full physics. There's the black box, where just you put a neural network, no physics. And there's a gray box, where you have a mixture of them. And depending on the application, you might need to use one or the other. Then we talked about control. So control is after you have a model for your device, you can then put it in an optimization software and design your pulses. The main challenges we have is machine learning challenges. So if you want to create a data set, in experiment, it takes time. In simulations, it also takes time. So it according to the system. In some systems, like solid state, it will be very quick to calculate, to perform measurements and measure Paulis. In photonics, it's slow. Whereas in simulations, if you want to simulating a photonic system is quicker than simulating a solid state system. So data sets is always a problem. And the other problem, again, of machine learning is computational efficiency. So how long, like we train these structures on supercomputers, because they're huge data sets and can just do it on your laptop. So when you have like your quantum system is large, then it becomes a big challenge. Okay. And finally, that this kind of research is important for both theory and experiment. So for theory, you can understand things about your system, your dynamics, and so on. And for experiment, because it gives you better information about the model, the actual model that's affecting your device. So this kind of research using the Graybox needs both theorists and experimentalists working together, actually. So it's not just theory or just experiments. With this said, so the final thing I want to say is that if you're doing theory, you use a Graybox. If you're doing experiment, use a Graybox. If you're doing both like me, then also use a Graybox. Okay, so this is the take-home message, and yeah, thanks very much.
That was very interesting talk, actually, Akram. Thank you very much.
Thank you.
All right, before so I'll have a couple of questions first. Then
Yes.
I'll ask others to ask if
Yes,
they have
please.
any questions. So, how scalable is your approach, Graybox approach? You already
Mhm.
mentioned that it's a challenging thing because of computational efficiency.
Yes.
But the reason why I'm asking this is because since like a quantum system has grows exponentially with like increasing number of
Yes,
systems,
exactly.
right?
Yes.
When
Mhm.
you're trying to do this in a classical or some sort of a semi-classical system, it will be very difficult, right? So how does it
Yes.
scale? Yeah.
So what you said is true, actually. So because in order to get these things correct, you almost do process tomography. Like the kind of measurement that is required is process tomography, and we know that this grows exponential with the number of qubits. So
Right.
this is a big challenge. So the workaround is to only characterize single and two qubit gates, because at the end we know from universality of quantum computing that any gate can be decomposed into a single and two qubit gates. And so this is the workaround. If you want to characterize two qubit gates, it's still possible, because now you have like 16 measurements, essentially, like all the Pauli combinations. So doing this on single and two qubit, I think, is still feasible. And once you characterize single and two qubit gates, then if you want to build like a bigger gate, you just decompose it. But as you mentioned, yeah, this is a challenge. Uh, if you want to have like a full characterization for more than 2-3 qubits, it's because everything explodes, and especially with machine learning. So machine learning classically works perfectly, and now we have ChatGPT and all of this stuff for one reason, because we have a lot of data and a lot of computational power, and data is very important. So you can just download millions of images on Google for cats and dogs. In quantum, it's not that easy because you have to do an experiment. So so this is, yeah, a fundamental limit from just the nature of machine learning. And so what I see is that this is a, like, my vision is that this is for NISQ devices. You have a few qubits and you can characterize pairs of qubits, and this would be sufficient to characterize the whole system. So this is one approach. The other approach is to combine this with error correction. And so in this case, you don't care about all measurements, you just care about the syndrome measurement. So there is one particular measurement that you want to characterize and know exactly. So in this case, it will be efficient because you don't have to do the full process tomography. Just measure the syndrome, train the Graybox to predict the syndrome, and that will be sufficient. So these are two approaches to work around the exponential explosion of quantum information when you're presented as a neural network.
Okay. The other question that I had is how greedy for data is your model? Like, because if you're actually performing experiments, right, you may not have as much data as a typical
Yes.
neural network would require, right?
Yeah.
So how greedy is your algorithm for data?
So I think so far the data set sizes we're using are doable. Like, we did the photonic experiment, and this is the slow one, and we were able to do it. So with solid state and superconducting qubits, it's even faster than photonics. So I think it's feasible. So we were working on, I think, size of like 10,000 examples, and this can be done in, like, again, according to the system, but like 1 or 2 days of measurement, or maybe even much less. So and this was sufficient. So the thing is, it's a trade-off. Okay. The more you have data, the better it is. If you have limited data, this will affect your MSE. But again, at the end, what you care about is not the MSE, it's actually the control fidelity. So if you work with 1,000 examples and data set size of 1,000, and you get control fidelities that are acceptable to you, then okay, go with it. You don't have to do like 10,000. Yeah.
So the other thing is,
Yeah.
sorry. When you say,
So,
sorry, you continue.
So the thing is that this is why you need, like, this is typical machine learning. So you have to, like, we have to work theories and experiments close to each other. I cannot just say, okay, yeah, let's do 10,000. I don't know. I need to train my model and see the performance and then send to the experimentalist to check the fidelities, and then we'll decide whether this is sufficient or not. So this kind of work needs collaboration. You cannot just give one party the whole job to do it. We need people working together.
So the other thing is, when you talk about selectable physics, right?
Yes.
About the Graybox model, you actually don't bring in a quantum system into the loop, right? So you don't have to really sort of interface a quantum system with a classical system as such, right?
Yeah, you don't. You just collect the measurements and send it over the email to
right. So,
me.
So your model doesn't suffer from the measurement collapse thing that a typical quantum machine learning model would require, because a quantum machine learning model would essentially need several shots, right? Typically, because of the measurement collapse.
Yes.
All right.
So yeah, you don't need to. It's not continuous measurement. You just do strong projective measurements and repeat for the number of shots, and like the typical characterization experiment that you do for yeah.
That's the only questions I had. Anybody else have any other questions?
Can I ask one question?
Yes.
Yeah. So in your model, the Graybox model mainly, so have you considered the lossy behavior of the waveguides?
No, we didn't. In this work, we didn't. So we modeled the device as closed system unitary. So we didn't model the losses. But again, this is what we are talking about how to design the gray box. You can design another gray box that takes into consideration that there are losses, and then you have to modify the structure so that it's not a unitary anymore, because you are losing photons. So it's like an open quantum system. So in principle, yes, you can do it. But yeah, in the work we have done, we didn't consider the photon loss.
Okay, thank you.
Thank you.
Any other question from anybody else? If not, thank you so much, Akram. It was a wonderful talk, and it was our pleasure to have you. We look forward to having more talks from you. And if you plan to, visit India some point, to come and visit our center, we would be happy to host. And is there? So, Professor Das, are you there? Would you like to have a word with? Longer here. Okay. Anyways, Akram, keep in touch, and we look forward to having more talks with you.
Thanks very much for the opportunity, and yeah, I'm happy for giving the talk today. Thanks very much for the invitation.
Thanks a lot. Okay. All right.
Okay. Thank you.
Bye.
Bye.